Hello, my name is Rogério, and this is Sampling Strategies to create moving regions from real-world observations. Let's start with some background. Basically, there are two models that can be used to represent spatial temporal data, the discrete model and the continuous one. In the discrete model, data is represented in a discrete way by the association of spatial information, like position and shape, to time instants. This representation may seem the most straightforward one, as real data is acquired in discrete snapshots. Although easy, the use of discrete model may lead to accuracy, storage, and performance issues depending on usage resolutions. Also, as real-world moving objects may change their position and shape continuously over time, there are applications where it is also necessary to represent these properties at any time, including in between observations. And this may be an issue when we use the discrete representation. Now, let's talk about the continuous model, which is another possible way to represent spatial temporal data. In this model, objects are represented using abstract data types, like moving points, moving lines, and moving regions. In this work, we deal with moving regions. In the continuous model, a moving object is represented by a geometry and a function. The geometry is used to represent the object's shape and position at a certain time, and the function is used to represent its evolution. In this figure, we present the object representation at two time instants. The intermediate representations would be like slices of objects' spatial temporal evolution. Then, if one has two observations, interpolation functions are used to estimate the region's intermediate position and shape at any time. This is known as the region interpolation problem. When compared to the discrete model, the continuous model representation provides potential gains in terms of data management, including compression and spatial temporal operations. Most of the work in the continuous model uses synthetic datasets. In this work, we studied how to use the continuous model to represent real-world data. Specifically, we are using images captured by drones. Some samples of these images are on the clips we present in this slide. They are part of a 15-minute video of a controlled fire. The clip on the left is of the beginning of the video. The second clip is of the middle of the video, and the third one is of the video's end. The full video is available to download at our project's website. Then, considering such images, how can we use the continuous model to represent the burnt area evolution? As we'll present later, there are several parameters to be studied, including object representation accuracy, snapshot sampling strategies, and noise detection. So, let's now see what would be a basic workflow for moving regions creation at database level. The first step on this workflow is data acquisition. As mentioned before, the considered video sequence has about 15 minutes. It was recorded using a 25 frames per second rate, which leads to more than 22,000 frames. Then, we made frame extraction and applied segmentation to identify the burnt area at each frame. We generated well-known text representations of the contours of identified burnt areas. Such well-known texts represent the burnt area polygons, and our intention was to load them into a DBMS and create the moving region representations. But then some questions arise. The first one is related to accuracy of representation. The polygons resulting from segmentation had an average number of 2,000 points. This leads to more than 43 million points to represent the entire dataset. Such number of points would impact on the performance of spatial temporal operations. There exist in the literature several simplification algorithms that could reduce the number of points used to represent each polygon. But how would polygon simplification impact on region interpolation quality? We evaluate the use of two well-known simplification algorithms, Douglas-Pilker and Wieswanger-White. We also tried two simplification levels for each of those algorithms. In this slide, we can see the original Burt area representation at a certain time and the other four representations generated using the simplification methods. Visually, we can verify that most of simplified representations provide reasonable accuracy, being the DP10 representation the worst one. We also compared the simplified geometries with the original ones in terms of number of points, Jacquard index, and Hausdorff distance. DP10, which is the dataset resulting from the use of the Douglas-Pilker algorithm with a tolerance of 10, achieved the largest simplification, reducing the number of points per geometry to just about 4% of the original one. On the other hand, the similarity to the original geometries in terms of Jacquard index was almost 3% worse than achieved in the other simplified datasets. Besides DP10, all the other configurations achieved an average Jacquard index of over 0.99, which is really good. The values of Hausdorff distance indicate that Wieswanger-White algorithm generated some local deformations. But the values of the Jacquard index indicate such local deformations would be relevant to our work. Let's go back to our data preparation workflow. After segmentation, we got more than 22,000 observations. In the continuous model, we use interpolation functions to simulate the evolution of spatial temporal data. Is it possible to select just some of the observations and still get an accurate representation of the burnt area evolution? For instance, consider these blue polygons. They represent the spatial temporal evolution of the burnt area between two snapshots and were obtained using an interpolation function. Are these representations accurate? How can we identify the observations to be selected in a dataset with more than 22,000 geometries in order to achieve good interpolation results? In order to identify the key observations to be selected, we propose the use of a dissimilarity distance-based strategy. We propose that the dissimilarity between two selected observations should not be too large, otherwise the interpolation function may fail to create good representations. Basically, in our algorithm, we compare two geometries and compute the dissimilarity distance between them. If such distance is considered too large, then we select the last pair of observations with an acceptable distance value. Let's see an example. Consider this set of geometries that represent a series of observations on the evolution of a moving object. We start by comparing the first two and evaluate if the dissimilarity distance between them is greater than the allowed value. As the distance is not too large, the next step is to compare the first and the third observations. Then, we compare observations number 1 and number 4 and still get an acceptable value for the dissimilarity distance. But the dissimilarity distance between observations number 1 and number 5 is considered too large. It means that the fourth observation should be selected, as it has an acceptable distance to the first one. Now, we should compare observation number 4 with its followings. We get acceptable distance values until we compare observations number 4 and number 7. Then, observation number 6 should be selected, as its distance to number 4 is acceptable. We should compare observation number 6 to its followings. We compare geometries number 6 and 7, and then we come to observation number 8, which is the last one. The first and last observation should always be present, as we use interpolation functions to create the spatial-temporal evolution. Then, we now have the set of selected observations that would be enough to represent the entire dataset. So, we use the dissimilarity distance-based approach to select the key observations in the original datasets and in the 4 datasets of simplified geometries. Then, we used an interpolation algorithm from the literature to generate the burnt area representation at time instants corresponding to the observations we didn't select. We compared simulated geometries with the real ones. The number of selected observations decreased as the threshold value for maximum distance increased. When using the maximum distance of 0.2, the number of selected observations was of about just 8% of the original number. The geometry simplification level of the dataset was relevant when we used small values as distance limits. The number of selected observations was highest in the most simplified datasets. But when we increased the maximum allowed distance, the simplification level became irrelevant in terms of the number of selected observations. We compared simulated geometries generated by the interpolation algorithm with original ones, computing the Jacquard index between corresponding geometries. In most of evaluated configurations, Jacquard index values were more dependent on the maximum allowed dissimilarity distance than on data simplification level. Then, we also compared our distance-based approach to uniform sampling. Uniform sampling, equidistant observations are selected. After selecting the key observations, we used an interpolation algorithm from the literature to generate the burnt area representations at time instants corresponding to the observations we didn't select. And we compared simulated geometries with the real ones. We evaluated the use of uniform sampling using several values for the sampling rate. The sampling rate defines the compression rate to be achieved, but provides no guarantee in terms of interpolation quality. We also compared the interpolation quality obtained when using uniform sampling and the one obtained when using the dissimilarity distance-based algorithm. To make such a comparison, we choose the configurations which provided similar compression rates. When using a similar amount of samples, the dissimilarity distance-based approach leads to better interpolation results than uniform sampling. We identified that in some situations, the proposed distance-based approach selected 3 geometries in sequence. This happened because some polygons are too distant from their previous and following ones. This is an unexpected situation as the burnt area should grow smoothly. By making a visual analysis on some of those situations, we identified such great difference was generated by problems in segmentation. We made some initial experiments on removing the observations that are too distant from their previous and following ones. For instance, consider these 3 observations. We removed the one on the middle from the dataset and ran the dissimilarity-based algorithm. The result was that the algorithm selected just observations 779 and 811 to represent all the remaining 32 observations between them. That confirms higher compression rates can be achieved when removing inaccurate data from the dataset. This work We present a real-world dataset based on images captured by drones. We evaluate the use of geometry simplification algorithms. We propose a new algorithm to select the key observations to be used when creating the moving region representation. We evaluate the use of the proposed strategy over datasets with distinct levels of object simplification. We compare the proposed strategy to another one in terms of compression rate and interpolation quality, and use an interpolation function to simulate geometries and compare them with the real ones. The interpolation algorithm generates in-between representations that are similar to real ones. Our similarity-based strategy achieves good compression rates, leads to good interpolation results, and helps on the identification of possible outliers. We showed that the simplification level may influence on the number of selected observations if we use low values for the maximum distance allowed, but it becomes irrelevant when the maximum distance allowed increases. As future work, we plan to study noise and outlier detection in the context of dataset preparation to the continuous representation of spatial-temporal data. We also plan to use obtained parameters as part of studies on fire and smoke propagation. Specifically, we intend to simulate the butt area evolution when there is no real observation. Thanks for your attention. You can find more information about our work in our project's website.